So in the original question, first we consider D is a, oh yeah, same problem. Yeah, thank you. Let me know. Yes, button. Yeah. When I do the zoom, yeah, but when I share the screen, yeah. All right, button. The first time, D is a non-negative integer. Now let's say in this way, non-negative integer, D, the first time. So we show this result. N to the D, this is a power function. It belongs to little o of a to the n. Right. But this result can be extended to non-integer. What's your name?
CJ.
Oh, CJ. Oh, yes, CJ. Okay. Yeah. So let me check your name later. Yeah. All right. Yeah, but if we can only use this result for integers, then it's too restrictive. Yeah, because sometimes we need to use it for non-integers. So here, we also want to prove if we remove the integer condition, so extend it to, let's say, positive number. How about that? So we extend from non-negative integer to positive number, positive real number. How can we show this result? Same result. Yeah. So that's the question, first question we need to answer. Okay? Yeah. But when we do that extension, there is a technical problem. What's the technical? Because when we apply L'Hopital's rule, look at the end, we need to do D factorial, integer factorial. Yeah. For non-integer, then factorial has the problem, right? For non-integer number, how do you define factorial? Okay, yeah. Although in calculus, there is a way to define factorial for non-integer numbers. Yeah. It's a gamma function. Gamma function, that's the extension of factorial. Okay, yeah. But here we do not go that far. Okay, we do not use the gamma function here. So here the question: we cannot use the factorial. No. So we have to find a different way to prove it. Yeah. The good thing is we have already proved the result for the integer. Can we use it? Right? So for the non-integer case, let's build our non-integer result on top of integer result. How about that? Okay? We have the integer result, so we can use it. All right? Yeah. All right. So let's do it. Okay, for non-integer case. For non-integer case, we need to do one technical treatment. One small technical treatment. If D is not an integer, we consider this case. What do? We do a special treatment. We use a special function to convert it to integer. We use the ceiling function. The ceiling function of the is an integer. Okay? Yeah. Or here, because here our D, yeah, so although here we use this one. Yeah. Any question? All right. Is an integer, right? Or positive integer. Okay? Yeah. Ceiling function. Now let's do this way. In order to calculate the limit, so let me write. After I write this formula, you can see the new result immediately. our goal, we calculate the limit, right? The goal, based on the little o notation. The meaning is its limit equals 0. So our goal, we want to calculate this limit, n to the d over a to the n. All right. Now, I split this limit into two parts. Split it. Okay, two parts. All right. The first part, limit n to the d over n to the d ceiling function. How about that? N to the d over n to the d ceiling function. How about that? All right. The second part, n to the d ceiling function over a to the n. Because the numerator here, denominator here cancel out, right? Yeah. One at the bottom, one copy at top, one copy at the bottom. We can do cancellation. After cancellation, the same as the original ratio, right? Original ratio. Here, we insert a new function. The new function is n to the d ceiling function. Okay? Yeah. Then split. After the split, the second limit, the exponent is integer. So we can use our older result. The second limit equals 0, right? The first limit less than equal to 1, right? Less than equal to 1. Yeah. All right? Yeah. Because when n equals less than equal to 1, yeah. Because when d and d ceiling function the same, they are equal. Okay? If it's different, smaller than 1. Okay? Limit is 0. So the limit can only be two cases, 1 or 0. Okay? Yeah. No matter it's 1 or 0, that number times the second 0 also 0. See? So this limit equals 0. So you can see, in this way, we complete the proof for non-integer d case. That means we can apply it to non-integer d. Okay? Yeah. Non-integer d, so this number actually we should change to greater than 0. Yeah. Greater than 0. We do not require that d greater or equal to 1. D greater than 0. Yeah. Because if d greater than 0, when d is 1/2, that means the root of n belongs to little o. That's also correct, right? Because sometimes we need to consider root of n. So we do not require d greater or equal to 1. Okay? We only require that d is positive number. Then this result is correct. Okay? Yeah. All right, so that's the discussion of this example, 2.5. All right. And this example, later we will see, this result I mentioned last time. In our homework assignment number 1, you will have a question related to this result. Yeah. Regarding the homework assignment, let me tell you the specific date I will give you. Wednesday next week. Okay? Yeah, next week. Yeah. Because we need to finish module 2. So this week we finish module 2 today, after today. So we'll finish module 2. Then next week we will finish part A, part B of module 3. So then we are ready to do the first assignment. Yeah. So the assignment date Wednesday next week. Okay? Yeah. 25th. Yeah. All right. Yeah. Next question. Yeah, so the next question, yeah, so let me erase a little bit. All right, erase a little bit. Yeah. Log base 2 of n belongs to the little of root of n. Root of n. Okay, yeah. So here, we just apply L'Hopital's rule another time, right? Yeah, so here, let me just apply L'Hopital's rule another time. But we need to work on continuous variable version of functions to take derivatives. Yeah. So here we use x replace n. X here we mean the value we can take continuous values. Yeah. So then these two functions we can take derivatives. Yeah. All right. So the derivative, yeah, before we take the bottom, the root function, we write as a power function, okay? X to the exponent number 1/2, power function. Power function, we have the formula, yeah, derivative formula, right? Yeah, so the power function. Derivative by the power function formula, 1/2 times x to the negative 1/2. Numerator, the formula, okay? Formula of the derivative of the log function. Yeah. Yeah. Log base 2. So the natural log of 2, that's a positive number times x. Yeah. Then let's simplify the representation. Yeah. So after the simplification, we have this form. Yeah. Before we apply the L'Hopital's rule, we see it's infinity over infinity indeterminate form. But at this point, it's not infinity over infinity indeterminate form. Yeah. So we cannot apply L'Hopital's rule the second time. So at this point, we can calculate the limit directly, yeah, because the numerator is constant, denominator when x goes to infinity, denominator goes to infinity. A constant over infinity, we know its limit is 0. Yeah. So we get this, the limit is 0. Yeah. So this is a continuous version limit. Then we go back to the discrete version. By the limit definition, we can go back to the discrete version. Yeah. Yeah. So the discrete version tells us when n goes to infinity, that log base 2 of n over root of n equals 0. So that's the discrete version. Okay? Yeah. From this, we can conclude little. Okay? Log base 2 of n belongs to little of root of n. Okay? Yeah. So that's the example number 2.6. All right. Last question of this part, 2.7. Yeah. So now, similar to the previous question, but we modify slightly. Okay, log base 2, we use the natural log. Okay, natural log we can simplify a little bit because in calculus we know if we use the natural log, many computation much easier. Many computation related to derivatives and integrals would be much easier. Okay. So here we use the natural log here. Yeah. But the result you can apply to any log base. Any log base A with A greater than 1. Yeah. It cannot be less than 1. Okay, it must be greater than 1. Okay? Yeah. So you can apply to, yeah. So this result, after we prove it, you can apply it to any log base A with a greater than 1. All right, yeah. And little of power function here, n to the d. Here, what's the d? D power function d greater than 0. Okay? We only require that d is positive number. Positive. Then we have this result. Yeah. So d is positive. Okay? Yeah. Oh. How can I remove it? That's interesting. Yeah. I just wrote it. Yeah. All right. Yeah. Let's prove it. L'Hopital's rule. Okay? Yeah. Same L'Hopital's rule. Yeah. Yeah. Continuous version also. Yeah. Derivative of natural log function, you can see it's very simple. It's a reciprocal function, 1 over x. Yeah. Denominator, derivative, power rule. Yeah. Power rule. Okay? Derivative, the power of derivative. Yeah. So d times x to the d minus 1. All right? Then we do simplification. After simplification, the fraction is 1 over d times x to the d. Yeah. Before we apply the L'Hopital's rule, we can see it is an infinity over infinity indeterminate form. But after the simplification, it's not an indeterminate form. Okay? So we cannot apply L'Hopital's rule another time. Yeah. We just calculate the limit directly. Yeah. The numerator constant 1, denominator, when x goes to infinity, it's infinity. Because d is a positive number, okay? X to the d is a positive number. So this power function also goes to infinity. 1 over infinity, its limit is 0. Then we go back to the discrete version. Yeah, the discrete version here we skip, but we can go back to the discrete version. We can get this conclusion. All right. Here. All right. So we finished the example part. Yeah. So you can see all these examples, we apply L'Hopital's rule. All right. Yeah. But I mentioned before, in our assignments, I will not give you a question asking you to apply L'Hopital's rule. Yeah. So you do not need to worry about that. Yeah. So you only need to, after these examples, you only need to apply the examples derived by L'Hopital's rule. Okay? Yeah. So then, in our homework questions, these two results are very important. So let me make the conclusion talking about these two important results in your homework assignment. The first one is this one. N to the d belongs to little of a to the n. What's the meaning of that? Okay? Yeah. So you need to use this result directly. N to the d. Compare these two functions, which one increases faster? All right, yeah. The second result is this result. Log function, log of n, belongs to little of n to the d, the power function. Okay? These two results, very important in our homework assignment. Okay? All right. Because you will see, so let's look at the first result and the second result. The first result, n to the d belongs to little o of a to the m with d positive a greater than 1. Okay? Yeah. So this result. Then we only need, so based on, because this D, we can use a different number, right? If only it's positive. A, we can use different numbers. If only A is greater than 1, right? Yeah. Then the question could be like this. N to the D, can I choose the D a large integer? Yeah, so here. Yeah, I just choose D as large integer. Let's say 1 million. N to the 1 millionth power function. 1 million. So this function increases very fast, right? Yeah. Raised to 1 millionth power. Okay? All right. Then the second function, A, because we only need A greater than 1. That's the only condition we need, right? So for that A, can I choose A very close to 1, slightly greater than 1, but very close to 1? How about that? Okay, that's 1.000001. How about that? Okay, only that 1 millionth more than 1. Okay, 1 millionth more than 1. Then raised to nth power. So it's an exponential function. Then I ask you, which function increases faster in the long run? Okay, in the long run, when n is very large, which function increases faster? Because the question like this, based on intuition, so many people, when they answer questions, they use their intuition. The intuition may give you the impression, the first one, so large, n to the 1 million. The second one, the base is very close to 1. 1 to the n is 1, right? Always 1. But here we just increase the base number slightly more than 1, then the exponential function is different from base 1 case, right? So in this situation, you can see the result could be different. How different? Look at this result. If you want to know what's the answer, you need to apply our first result. Okay? So that's the first question. The second question. Compare log function, log of n. Okay? Log of base. Here we use a hidden base. Okay? Hidden base, you can understand positive constant a greater than 1. The hidden base a greater than 1. Okay? A with a greater than 1. That hidden base. Okay? All right. Then you compare n to the d power function. Now we compare, because the power function we only need d greater than 0. So how about n to the 0 point, a very small number. N to the 1 millionth, that's small number. Okay? When you compare these two functions, if you still use your intuition, because when the exponent number is extremely small, your intuition could be this function value very close to 0, right? Very close to 0. But think about our n can grow as a very big number, huge number, the exponent number, although it's very small, but our base number so huge, it can eventually overcome the small exponent number, right? It can overcome it. All right, think about that. Okay, yeah. So then, when you compare these two functions, you need to connect to the result of our example 2.7. Okay? Now, so these two questions you need to answer in the coming homework assignment next week. Okay? Yeah. All right. So we finish part C. Let's move to part D, the last part of module 2. All right. Title, brute force method. We used before, so here, when we, talk about this method in general first, then we use it to solve a few questions. All right. D.1 Introduction to brute force method. First, the description of the brute force method. Let's look at the, main properties of this method. First, it's a straightforward approach. Brute force. So you do not need to do anything special to solve any given computing problem. So when you start, you do not apply any technique, special technique, okay? Just to work on the problem in a straightforward way, okay? All right, so without any manipulation, so work on it directly. All right, so you can always apply it to a problem. The result usually may not be good, but at least you can do something, okay? Yeah, it's better than nothing. You can do something. Okay. So in general, it is not the best algorithm. No, the brute force. No. Actually, in general, it's not a good one. No. No. So, no, yeah, definitely, in general, not the best. No. It is usually used as the starting point for more advanced algorithm. Yeah. So why many people, they still want to start with the brute force method because they want to understand the given computing problem better. At the beginning, a lot of hidden properties, not that obvious. So they want to explore. Yeah. So they want to, work on the problem, and when they work, they can discover some special properties. So that's usually what people do. Yeah. So get some experience by using this simple method. All right. The efficiency difference between the brute force method and the more advanced algorithm could be huge. Yeah. Because later we want to find a much better, much more efficient algorithm. Yeah. Yeah. Because we know the difference of efficiencies could be huge. Yeah. The example is this polynomial evaluation problem. Polynomial evaluation problem, what is the difference of the efficiency function? Yeah. So these two functions. By Horner's rule, it's n. Yeah. If you apply Horner's rule, you get n. But if you apply the brute force method, 1/2 n times n minus 1. That's the difference. Okay? All right. All right, so now let's work on another computing problem. This one, the problem 4, we revisited. So we did a selection sort before. So this time we want to solve it in a different way. So we do it with a different solution. Okay, all right. Given an array, how to sort it in ascending order. Our old question, but this time we want to apply a different property, a property different from the first time. So some of you may ask, we have solved it, so why do you want to do it again? So the reason, usually the question, so why we solve the same question repeatedly, so usually the reason, 2 basic reasons. The first reason, we want to improve it. That's one of the reasons. Right? We want to do better, so improve it. That's the first reason. Second reason, sometimes we may not be able to improve it, but we want to solve it using a different method, algorithm, because there is another important understanding related to problem solving. In problem solving, thinking is very important. The way of thinking. How do you think? How do you do the analysis? How do you apply your logic reasoning to solve the problem? That's very important. And we can see for different solutions, the logic reasoning paths are different, right? The solution paths are different. And those different solution paths, they are valuable for your future problem solving, right? Your future problem solving. You may need to borrow, some parts here and there, different places from your experience, different logic reasoning methods you want to use in your future problem solving. From that point of view, we treat multiple solutions for the same computing problem is valuable. Okay? Valuable. Okay. All right. So why we need to solve it another time? Because a problem, we can treat it, understand it as a carrier of a set of thinking methods that result in different solutions. So one problem here, sorting problem. This one sorting problem, it can carry, this problem carry 6 different solutions. Let's think about it. Because this semester we will learn 6 different solutions. Okay? We will learn 6 different solutions. So this problem carries 6 different problem-solving methods. Okay? So those problem-solving methods, they are valuable. Right? But we need to use this one problem to carry those 6 different methods. How about that? So that's another way to view why we want to try different solutions. Okay, all right. The thinking methods are important to help us solve other problems, future, other computing problems. Yeah. So that's our experience. All these older solutions, they become our experience. Yeah. So in our future problem solving, then we build our new solution on top of our experience. Okay, all right. Yeah. So here, let's solve this question again, but we need to discover a new property. This time, we should view this question differently from our first time. First time, we used the minimum, finding the minimum, that view. Here, do not go that direction, okay? If you go that direction, you will get the same solution. So let's go from a completely different direction.
So the one we're going to find, is that any better than one?
Yeah. We don't know. Yeah. At the beginning, we don't know. Only after we complete the solution, we can do the comparison, right? Yeah. Before that, we don't know. Okay? Yeah. All right. Let's make our observation. Yeah. We need to find a different property. Yeah. What is that property? The critical property. We need to discover the critical property. Yeah. So that's the insight, right? We need to get that insight, the critical property. Yeah. All right. So let's draw a diagram. So this is a general array. Yeah. For the general array, because we need to do comparison. When we do comparison, we compare two elements in the array. When we do that comparison, we need to study, okay? For any two elements in the array, we need to study which one larger, which one smaller, okay? There are only two cases, right? Yeah. When we compare two elements, there are only two cases. Yeah. Yeah. And the two cases, yeah. The first one, A less than or equal to B. We put equal together with less, okay? Less than or equal to B. Then we can reduce one case, okay? The second case, A greater than B, okay? These two cases. And which of the two cases is closer to the definition? What's the closer to the destination. What is our destination? In a sorting problem, what is the destination of our solution? Path, solution, destination. Array in ascending order, right? Yeah. Because at the end, we make an array sorted. The array is arranged in ascending order. That's the destination, okay? Now tell me, which of the two cases can make us closer to the destination? The second one, all right, so here, so let's say, at the beginning, so the location, A in front of B, all right? Yeah, because two elements in the array, they have their locations, right? Yeah. So let's assume A is before B. How about that? A is before B, okay? Yeah. So when you go through from left to right, you see A first, then you see B, okay? That's the two locations. Then, the first case, A less than or equal to B. Second case, A greater than B. So which one would lead us closer to the destination? The whole array is ordered. First. Yeah. Because the first one, A less than or equal to B, they are in order, right? They are in order. matching the destination order. Destination in order, right? Yeah. So the first one has the same order as the destination requirement, right? The second one is opposite. The second one is against the destination order, different. So the first one, we wish to have the first case, and we want to avoid second case, right? Yeah, we want to avoid second case. So the second case, we need to fix the second case. Okay, so if the second case happens, yeah, because it's against our destination situation, so we want to fix it. We want to change it, fix it. Yeah. So the second case, we want to study. The first case, it's good. So we do not need to do any more work. Okay. The second one, in order to fix it, you need to do more work, right? Yeah. So we want to focus on the second case. The second case, the location order and the value order are different, right? Location order, A is before B. That's the location order. The value order, A is after B, right? If you arrange in ascending order, A is after B. So the location order and the value order just the opposite. Okay? So we introduce a new concept describing this situation. The new concept is called inversion. Inversion. Okay? Yeah. So here, all right. Out of order. Yeah, because we look at, yeah. If the given array is not in order, then you need to consider two of the elements may be out of order. That situation. So let's study that property. That property. The property is, if the array is not sorted, there must be two of the adjacent elements that are out of order. Can you see that? If array is not ordered, there must be two of the adjacent elements out of order. Think about it. If the statement is correct or not. Correct or not. All right. In order to see it clearly, because it's not that obvious. At this point, it is not that obvious. So we need to understand it better. All right. Yeah. So here, in order to understand better, so here, let me introduce this concept, inversion concept. Inversion concept. So what's the inversion? For a pair of elements in the given array, this pair, you select arbitrary two elements from the array. A sub I and A sub j is, if this pair is called inversion, then we need to check the condition, given this condition. If I less than j, the subscripts, subscript I is less than subscript j, that means the location. Location is in order. Yeah. A sub I is before, in front of A sub j. Yeah. Then the value is opposite direction, in opposite order. Value is in opposite order of the subscript order. Okay. Subscript in normal order. Okay. The value is in opposite order. The value A sub I value is greater than A sub j value. Opposite order. So we call this pair as an inversion of this array. So we count. So this array has, regarding this pair of elements, there is one inversion. And then this array can have many other inversions, right? Many other inversions. Yeah. So we can count. How many inversions are there in a given array? So we need to count. Okay, all right. So if the array is sorted, let's think about if an array is sorted, is there any inversion? If array has already been sorted, is there any inversion? No inversion. Yeah. Because they are in order, you cannot find even one inversion. There is no inversion. Yeah. So that's easy to see, right? So, but if array is not sorted, then that must be at least one inversion, right? Yeah. If array is sorted, no zero inversion. But if an array is not sorted, there must be one inversion. At least one inversion. Okay? Yeah. All right. All right. So then, let's understand this. If an array is not sorted, there must be one adjacent inversion. Can you see that? They're not just inversion. We want to say adjacent. That means the two elements are adjacent, like these two. These two elements are adjacent. The subscripts, two consecutive integers, I and I plus 1, so adjacent. Okay? So here the statement is, if an array is not sorted, then there must be an adjacent inversion. A little harder to see, but to see it, yeah, here. How to see it? Let's apply the contrapositive method. You know contrapositive method, right? Yeah. This thinking is also important in problem solving. Okay? Contrapositive method. Contrapositive method thinking. In discrete math, you learn it. Okay? Yeah. Contrapositive method. So here, if we use the contrapositive method, so if array is not sorted, there must be an inversion. Yeah. So let's negate the conclusion. The contrapositive method, that we need to negate the conclusion first. So what's the negation of the conclusion? There is no adjacent inversion, right? That's the negation. Okay? Yeah. Think about it. If given an array, if there is no adjacent inversion, what can you say about this array? No adjacent. You cannot find any adjacent inversion. What can you say about it? Yeah, or sorted. Yeah, it's in order because no adjacent, when you look at every two adjacent elements, the second one is always greater than the first one. That means in order, right? Any two adjacent elements are in order. Can you say the whole array in order? By transitivity property, the whole array is in order. Here, we know that in order property is transitive. Okay? So by the transitivity property, the whole array is in order. So this is the contrapositive thinking. Okay? Contrapositive, if we negate the conclusion, then the hypothesis. Yeah. So this is a hypothesis. The hypothesis is different. The hypothesis is different. Okay? So if the array is in order, if the array has no inversion, or adjacent inversion, if the array has no adjacent inversion, then the array must be sorted, must be ordered. Must be ordered. Okay? Okay? Contrapositive, yeah, not assuming. So, yeah, we assume. So negation, we assume that. Yeah, we assume if the conclusion is false. So what do you mean conclusion is false? Array has no inversion. That means the conclusion is false, right? Negation. Yeah. If a conclusion is false, then The hypothesis is different, right? Different from the given one. Yeah. The hypothesis is the array is ordered. If it's ordered, then your original hypothesis is wrong, right? Original hypothesis is wrong, so you cannot get the wrong conclusion, right? Our hypothesis conclusion. So your hypothesis is wrong, that means your negation is wrong, so the original conclusion is correct. That's the contrapositive method. Here the logic. Here we use the logic. The contrapositive method is correct by logic. That's the pure logic. Pure logic has this logic rule. The contrapositive based on a logic rule.
Sorry, please. This is like the version of this is version PRA4.
Yeah.
That's it.
Yeah. Yeah. So that's why, yeah, because it is different from the hypothesis. That means our assumption of the conclusion statement is false. Then it's false. We need to change it to make it correct. Yeah. So the other side is true. What's the other side? The array must have at least one adjacent inversion. That's the logic. Okay, based on the logic. All right. Yeah. So after you understand that, then you can understand that property easily, right? Yeah. Yeah, because this one we didn't, the first one we didn't use the inversion concept. Yeah. Here we use the inversion concept, but this statement we didn't use. We say adjacent elements that are out of order. That's the meaning of inversion, right? Yeah. There must be two adjacent elements that are out of order. That's the meaning of inversion. But we didn't use the inversion concept here, right? Yeah, so that's the same thing. All right. Then, summary of this discussion. Summary. Okay? Yeah. This why? So here we discovered this critical property. Why it is useful here? Yeah. So we will apply this property to solve the sorting problem soon. Yeah, quickly. Yeah. Why this property is useful for our solution? Because if we do not use this property, in order to sort the whole array, we need to fix all the inversions, right? You need to fix all the inversions to solve the problem, sorting problem. But the inversion, when we talk about inversions, they are global inversions, right? The inversion, the two elements of the inversions can appear anywhere in the array, right? So the inversions we are considered, they are global inversions. Without using this critical property, we need to look at all the global inversions. But with this property, we do not need to look at the global inversions, right? We only need to consider the local inversions. Is that an improvement? Is that improvement? So our focus changes from global inversion to local inversion. Is that an improvement? Because if we only need to work on local inversions, we do much less work, right? If you need to fix all the global inversions, you need to do more work. Think about that. Okay? Global, okay? You need to, jump here and there, fix all the inversions. Think about that. The global work. But here we only need to do local work. Okay? Yeah. So you reduce the amount of work. After we change our view from global view to local view, you reduce the amount of work you need to do. That's the essence of this method. Okay, all right. Let's apply this idea to solve this problem. We only work on the local inversions. All right, yeah, so let's do it. Yeah. How to fix it? How to fix all the inversions? Okay, yeah. How to fix one inversion? We use swap operation, right? If you discover one inversion, you just swap two elements. You fix it. Yeah. So that's the, simple way to fix one inversion. Swap two elements. Okay, you fix it. Okay, all right. So let's implement our idea. Let's apply the swap operations to fix all the inversions in the given array. All right. Remove, our goal, we want to remove all the local inversions by local swaps. Think about it. If you can remove all the local inversions, you get the whole array ordered. You get the whole array sorted, right? If you can fix all the local inversions. Okay? That means after the swap operations, there is no local inversion. You get the whole array sorted. Okay? So that's simple. Yeah. But to do local swap, is that easy? You only need to do local swap. That's easy. Yeah. So let's do the local swap. Okay? We start from the first element. So we scan the array multiple times. Yeah. Every time when we start a scan, we start from the first element. First element. All right, so we compare two adjacent elements. When we compare, we do swaps one by one from left to right, if necessary. Okay? You do swap if necessary. Yeah. If the two adjacent elements are in order, you do not do swap. Okay? You do not do swap. Only when you discover the two adjacent elements are an inversion, form an inversion, you do swap. Okay? So you do swaps one by one from left to right if necessary. Okay? Yeah. Only when it is necessary. Okay? Yeah. Stop at the first in-place element. Yeah. So let's understand this step 3. Yeah. So what is this first in-place element? Yeah. Look at this. When you do adjacent swap operation, one by one from left to right, one by one, yeah. After you finish one scan from beginning to end, what do you get? Can you see any special property? So after you do one scan from left to right on adjacent pairs from beginning, which one you put in place? Which element you put in place? The smallest or the largest? The largest. Yeah. Because every time when you do swap, you make the larger one, you push the larger one to the right end, right? Yeah, you push larger element to the right end. Okay. Keep pushing. If you have a largest element somewhere in the array, you keep pushing it to the end. Okay? When you reach the end, the largest element is in place. Okay? Yeah. The largest element in place. Yeah. The second round, you push the second largest element at the current end. Yeah, because the first end, it's already in place. So you won't touch it anymore. Okay? So the first element, largest element, if it's already in place, the second round, you don't touch it. It's in place. Why you touch an element in place? Okay? Unnecessary. So that's the reason we stop right before the in-place element. You can stop before in-place element.
Switch only happens once.
Not once. The first time we put one element in place. So you do the second time, we put a second element in place.
Oh, yeah.
The third time, put a third, until we put all elements in place. Then you get sorted. Yeah? Because one scan not enough. Okay? One scan not enough. So you need to do n-1 scans. n-1. Because the last scan you do not need to do. The last scan you only have one element. So that is forced in place, right? One element is forced in place. Because the remaining n-1 elements already placed in place. Or they are already in place. They are already in place. So the last one is forced to be in place. So you need to do scan n-1 times. So you put all elements in place. Okay, yeah. So here, let's look at the summary. Okay, yeah. There is one element in place for every scan. That one in place, the maximum element of the current array. Yeah. Current array. Because each round we reduce the size of the current array, right? By elimination method. After you put one element in place, we eliminate it. Yeah. So here we apply little elimination method. Okay? Yeah. All right. Yeah. Yeah. So every time there is one element in place for every scan. Yeah. The in-place element of each scan appears at the end of the current array. Yeah, the largest one, the current array. Okay? All right. The current array is subarray that excludes all the in-place elements. It excludes all the in-place elements. Yeah, so that's the current array. Okay? Yeah. So these are the, all the meaningful properties for this sorting algorithm. We sort it. We get the whole array sorted in this way. Okay? In this way. This way, if you look at the adjacent swap operation in a visual understanding, visual way, we'll look at this phenomenon visually. Okay? Visually, it's like a bubble, right? A bubble, moving bubble. So this is the bubble sort. Okay? Yeah. You know the bubble sort. Many of you know the bubble sort, because we learned it in data structure class. Okay? 2250, the bubble sort, we learned it. 2250. Yeah. But at that time, we do not use this view, right? Inversion. Yeah. We didn't use inversion view to solve the bubble sort, right? To do the bubble sort. Yeah. Here, we revisit the bubble sort, but we use the new concept, inversion view. Okay? Yeah, that's the bubble sort. Efficiency analysis, similar to the selection sort. Yeah. Because you have to do that many scans. Each scan, you need to do the same number of comparisons as we did in the selection sort. So the efficiency analysis the same as the selection sort. So here I do not repeat. Okay? Do not repeat. Yeah. So the conclusion also the same. Yeah. The conclusion is the number of comparisons the same. 1/2 times n times n minus 1. This many comparisons. Okay? Thus many comparisons. And only one case. Okay, remember, the selection sort, we only have one case. Best case, worst case, average case, the same. Here, we have the same thing. Yeah. But here, what is the basic operation? Yeah. Comparison or swap? Yeah. So, because we use comparison and swap, both operations in this algorithm. But which one is the basic operation? Comparison or swap? Which one? We need to do more. We need to do more, this operation more times. Comparison or swap? More times. Correct. Correct. Yeah. Swap only when necessary. Think about, if given array already in order, do you need to do any swap? No swap. If the given array already in order, you do no swap, but you still need to do the same number of comparison, this number. Okay? That means the swap operation is the basic operation. All right, so we finished the D.1. So we have one question, D.2 left. So next time we will finish D.